All right, so the rest of this chapter is dealing with something called vectors, okay? Vectors are like rays with direction, basically. So we're going to learn a lot of stuff about vectors between 6.3, 6.4, and 6.5. Actually, vectors 6.3 and 6.4, and then something complex number 6.5. And then that's where the test material will stop, and where your test, which was next Thursday, will be. Which will include the 6.1 and 6.2. We'll have sines, we'll have cosines, and then the stuff that we're going to do now. Today, we're going to start this, and then tomorrow, you'll finish it, okay? So we're just going to introduce into vectors. So what is a vector? A vector, like I said, it's a segment because it has two endpoints with a direction. So it's a segment because of the two endpoints, but it's going to have an arrow to show direction. It almost is like slope, okay? So it's like a line with slope. The little arrow over, so this PQ is one way to name this vector, and that little arrow over it shows you which direction it's heading. So just like a ray in geometry, if you remember, the arrow has to be where the arrow's pointing. Because this arrow is over the Q, I would know that P, which is called the initial point, is where it starts, and Q is called the terminal point, where it ends. So when you draw a vector, it's got to have two endpoints. This does end, okay? So you can measure its length. It does end. But it also has an arrow to show the direction, and that arrow points in the direction of the terminal point. So if this had been QP and the arrow was over the P, then I know the arrow would have pointed in that direction, would have changed the direction on it, okay? So again, when you draw a vector, it's a segment. It has two endpoints, so it starts and stops, but it has an arrow to show which direction it's pointing in. The component form of a vector is almost like a separated out slope. So you have in order to find component form, you'll have an initial point and you'll have a terminal point. They're xy and xy. And you will take the terminal points x and subtract the initial points x from it. And then you'll take the terminal points y and subtract the initial points y. So it's x minus x, y minus y. And then in addition to the two letters like we just used to name a vector, you will also see it be named with a bolded lowercase letter. So a lot of times they'll use U or V or W. Those are just names of vectors. So you can either use the two letters with an arrow over them, or you can use a bolded lowercase letter. And notice these are not parentheses. When I show vector form or component form, so at the end this will be a number, comma, another number, okay? You will see them with the brackets around them, and that's how you know the difference between the actual component form and a coordinate point. So if I showed you this, that's a coordinate point, but if I showed you this is a vector with a horizontal change of 2 and a vertical change of 3. Anybody still coming down? Okay, so then this says the magnitude, and we find the magnitude by two different ways. One, doing the distance formula with our initial point and our terminal point, so that magnitude is the same thing as the length of a vector. You can either do x1 minus x2 squared plus y2 minus y1 squared if you have the initial and the terminal. Or if you already have component form like this, then you can do the square root of a squared plus b squared. And this should actually be doubled. This should be double V, double lines before the V and after the V. That's how you show magnitude. So that would be the symbol for magnitude, like a double absolute value. And the magnitude will be one number, okay? It can be a radical, but it would need to be simplified. But it's not separated by a comma like the component form is. Equivalent vectors are vectors that have the same magnitude and direction. So they have to have two parts, magnitude and direction. They can have the same magnitude and a different direction. So two vectors can have the same magnitude but different directions. But if they have the same direction, they're going to have the same magnitude. both would have to be true in order for them to be equivalent. So it is possible, again, it's possible for the distance between 2 points to be the same, but the slope of those points to be different. That's what magnitude would be the same, but direction would be different. But if the direction is the same, then the magnitude will be the same. So as long as they have the same direction, you'd know they'd be equivalent vectors. All right, example 1 says show that U equals V. So we just said what has to be true about the two vectors in order for them to be equal. Same direction, right? Or same direction and magnitude. So direction is component form. If I look at this vector, and it should have an endpoint there, okay? It's really hard to draw these. Then if I were to find the direction here, it's the change in x followed by the change in y. So that's the difference between component form and slope, right? So if I went from 0, 0 as my initial point to 2, 3 as my terminal point, and I know 2, 3 is the terminal point because that's where the arrow is pointing, then my component form would be 2 minus 0 and 3 minus 0, or 2, 3. Because it started at 0, 0, I could have also just counted, right? My change in x and my change in y. That's the component form, or the direction. When you look at the second one, and again, I would know that this is my initial point, this is my terminal point, because that's where the arrow is pointing. I can either count the change in x, 1, 2, change in y, 1, 2, 3, or I can find the component form by doing -2 minus a -4 and -1 minus a -4. And this becomes 2 and this becomes 3. So both have the same component form, right? Which means if I were to find each of their magnitude, and I'll show you how that's done, I could just say the square root of 2 squared plus 3 squared, which would be 4 plus 9, and that's square root 13. That's the magnitude of the orange one. And then here I'd get exactly the same thing because I'm squaring the same things. So when you're looking for equivalent vectors, as soon as you see that their direction is the same, that's you showing that the magnitudes, or that the vectors would be congruent. So you don't need to do both. You just need the direction. But they'd have to be the same. Just the magnitude being the same is not enough. But if the direction is the same, then the magnitude is the same. All right, this says find the component form and the magnitude of vector v. So A, the initial point's -1, 5, and the terminal point's 15, 12. I'll do A with you, and then you're going to do the B by yourself. So component form, we get by doing x2 minus x1 and y2 minus y1. In this case, this is our x1 and y1 because that's our initial point. This is our x2, y2 because that's our terminal point. So then I get 15 minus a -1, which becomes +1, 12 minus 5, 16, 7. That's the component form of this vector. Then I want to do magnitude. And remember, we said there's two ways to do magnitude. One is use the distance formula from the beginning. So I would get the square root of 15 minus a -1 squared plus 12 minus 5 squared. Continue to work that out. Or, less work, if I already have the component form, I do the square root of a squared plus b squared, a being the first term, b being the second term. So I get 16 times 16 which is 256 plus 49, or 305. It's the square root, but I need to make sure it can't be simplified, right? I know for sure 5 goes in here. It goes in 61 times. 61 is prime. So I can leave it as the square root of 305. All right, you do B. All right, so your component form, you should have done 5 minus a negative 3, which becomes plus 3 or 8. And then 1 minus a negative 5 becomes plus 5 or 6. So your component form is 8, 6. And then the magnitude, square root of a squared plus b squared, which is 10. This is actually a triple, right? A squared and b squared, c squared, 6, 8, or 6, 8, 10 would have been a triple. Those will always work like that. Question so far. So that is the foundation of like so many things in vectors. You have to know how to find the component form and the magnitude. You have to understand the difference between them, what that component form represents, because in a minute we're going to learn how to graph those. All right, a scalar multiple is a big long paragraph to say that a scalar multiple is a single number that changes the length of your vector. So if I said 2 times a vector, I mean take its length and double it. If I say 1/2 times a vector, I mean take your vector, cut it in half. Direction doesn't change if it's a positive number you're multiplying by. So if you look at what's on the bottom here, if I were to take, and this is when it's easier in Notability to do it, but if you look at it, right, this is single vector. This is vector v. If I then say 2 times v, and I took this vector, and if you copied it and pasted in Notability, you would see it be half of this, because if I double it, I get it to v. It goes in the same direction, it has just doubled in length. If you do a half, you've basically just cut that in half. So you took what was here, I said, okay, split it in half, and now it's that long. That would be 1/2 of v. Now the negative on the front, notice where that arrow points. On the first one, it was pointing up and to the right. What happens when I flip it so it's negative? It's pointing down and left. So the negative changes direction. If it started pointing down and I put a negative on the front as a scalar, it would flip the direction to point it up, okay? And that 3/2 means 1.5 times as long. So I've changed it so that it's 1.5 times its length, and I've also changed the direction of the arrow. So a scalar can change length and direction if it changes the sign. But a scalar by itself is just a number. Questions? All right. These are all the things you can do with a vector. You can, if you start with initial vector like uv, u2, and v1, v2, and then if k is a scalar, again, meaning just a number, then we can take two vectors and we can add them together by adding the first term in each and adding the second terms of each. And this will stay in component form, a number, comma, a number. We can take two vectors and subtract them by doing first minus first and second minus second. We can take a scalar and multiply it times a vector. So something like that would look like 2u, and that what that would mean is take 2 and distribute it into both parts of your vector. And you can take the numbers out of the vector, sign off the vector. So if I had negative v, it's the same thing as saying -1 times v. So here the negative just comes off and it gets represented by the -1. Sketching a vector. So when you are drawing a vector, realize that you're drawing, remember it's a segment with an arrow, right? So you will draw it as the first number is the change in x, the second number is the change in y. There's two kinds of problems with this. One where they'll give you the initial and the terminal point, and you simply plot those 2 points, connect them, put the arrow in the direction of the terminal. And then there's some where they give you the component form. You would start at 0, 0, and then use the first number as your change in x, and the second number as your change in y. All right. So this one says, and it's got multiple parts, it says find A, U plus V, B, U minus V, C, 2U minus 3V, and then sketch each resultant vector. So we're going to find A, which is U plus V first. U plus V says take the first U and the first V and add them together, so 2 plus 1. Then take the first V and the second U and the second V and add them together. And my resultant vector is 3, 4. With me so far? So if I want to draw this, you have starting at 0, 0, because I don't have an initial and a terminal, I just have the component form. I would go to the right 3 because that first number is my change in x, and I would go up 4, 1, 2, 3, 4, and that's my terminal point. Connect your 2, arrow in the direction of the end or the terminal point. The other way to draw this, U plus V, because sometimes you're going to have to do it from an actual drawn vector, not coordinate points, is if I had 2, 1 as the first one, I would have started at 0. I would have gone to the right 2 and up 1. That would have been that vector. And then 1, 3, right 1, up 3 would have been this vector. So this is U. And this is V. With me so far? I just graphed those. The other way to find the sum of these two is to continue each side out.
Teachers and students, pardon the interruption. At this time, we're going to begin our math.
Record. If I drew a line that was parallel to the bottom side coming off of that terminal point on the purple, and then I drew a line that was parallel to the purple side coming off the other one, then where they meet would be the terminal point of the sum. So I'll show you more examples of that on tomorrow's video, but that's kind of one of the ideas, is you have to add the two segments. I'm just going to finish this example real fast, so we'll go. B is U minus V. So I would do 2 minus 1 and 1 minus 3, which is 1, negative 2. The result of that would go start at 0, 0, right 1, down 2, and my graph would look like that. C, 2 times U minus 3 times V. So the first thing I'm going to do is take 2 as a scalar, multiply it into U, and then I'm going to take 3 as a scalar on V. So I distribute that into both. I get 4, 2. And then you can either distribute with the negative or without, it doesn't matter. But if I say minus and just distribute the 3 in, 3, 9. Now I'm doing 4 minus 3 and 2 minus 9, or 1, negative 7. If you had distributed it a negative 3, obviously you'd be adding at that point. And the result vector from here would start at 0, 0, go to the right 1, 1, 2, 3, 4, 5, 6, 7, down 7. And that would be what it would look like graphed. Questions? Okay, so we're going to stop there. The 6-3 homework is open. It will feel like a lot if you save it all for tomorrow, but you can get a head start on it today and then only have to do the end part tomorrow. That would be the wise decision because there's still 8 more slides.